Okay. Hi everyone, my name is Chao. I'm currently doing postdoctoral research at Tsinghua University. I'm very glad to be here to introduce my recent work, the new developed framework for weakly coupled ensemble data assimilation. And beside me is Dr. Liu, is the leader of our work and the leader of our vocabulary. Okay. This is the outline of my presentation today. Firstly, I'll give a brief introduction to our motivation. With the development of seamless prediction, data assimilation also needed to be upgraded from a single model to a coupled model. Ensemble-based DA methods such as EN or ENCAP or hybrid DA have been widely used in weather forecasting and climate prediction. These methods typically require the ensemble run of members. Besides scientific challenges about coupled DA methods, there are also key technical challenges from ensemble-based DA system construction. For example, how to achieve the ensemble run of a coupled model from its individual run, how to integrate the coupled model, ensemble, and the D method into one system, and how to exchange data between the model ensemble and the D method. The construction of offline D system is one of the most common solutions to these challenges. In this system, each model ensemble member runs as an independent MPI program, and the DA methods also accrues as an independent MPI run. The data exchange between them is always achieved by reading and writing restart fields. And the scripts are mainly used to control their cycle operations. This kind of system is easy to implement and keeps good independence of model and D method. However, our-based data exchanges program restarts will introduce higher overhead and larger ensemble numbers or final resolution, and finally will result in low efficiency. Another solution is an online D system, where the model ensemble and the D method are integrated into one single MPI run, and the D exchange between them is conducted by efficient MPI communication. Moreover, an online D system does not rely on program restarts, so it can achieve higher efficiency. Of course, there are many challenges. For example, how to conveniently integrate the ensemble and D method into one single MPI run, how to flexibly drive a D method by a model, and how to enable a D method to run on the process all ensemble members, and how to efficiently and conveniently exchange data. A good solution might be to develop a common D framework, which can be shared by various coupled models and D methods. We note that staff has set a good example in this aspect. As a coupled team, it's still very intriguing for us that whether the development of such a framework can benefit from existing couplers, especially LC coupler. In other words, can we unify a coupler and an ensemble D framework together? We note that almost all couplers can perform MPI-based data exchanges between computer models or into one computer model. Moreover, CCouple2 can integrate coupled models and implement their ensemble run flexibly. Most operations for achieving data exchanges can be generated conveniently by its automatic coupling generation. Of course, there are still challenges to develop a D framework based on CCouple2. So to address the remaining challenges, we designed a new framework, .cc, based on our CCouple. This figure shows its architecture. Besides CCouple2, it consists of 4 managers and a set of new APIs. Ensemble component manager mainly use the CCouple2 interfaces for integrating coupled models and generating communicators of their ensemble member. The algorithm integration manager enables the user to conveniently develop drawing interfaces for a DIM algorithm. A DIM algorithm program is compiled into a dynamic link library, and it will be dynamically linked to a model when an instance of the DIM algorithm is initialized. The online DIM procedure manager provides several APIs to enable a component model to initialize, run, and finalize DIM instances, and handles data exchanges between the model and the DIM algorithm. The ensemble DIM configuration manager enables the user to flexibly choose DIM algorithms and set parameters for a DIM experiment via the configuration file. So with this framework, a model can draw DIM algorithms and automatically exchange data among them by adding some API calls to its running flow. If a model itself uses TCAP2 for coupling, it can easily achieve ensemble DIM by adding the green part into figure, such as the registration of DIM configuration, the API calls to initialize, run, and finalize DIM instances. If a model doesn't use TCAP2 for coupling, only a few operations, such as the model registration in the gray parts of the figure, need to be further added to achieve ensemble DIM by using DefTC. In order to enable a model to drive a DIM algorithm via the API shown on the left, drawing interfaces of drawing subroutines of the DIM algorithm should be developed with the corresponding APIs. The drawing subroutines work for the initialization, running, and finalization of a DIM algorithm, where the input and output fields of the DIM algorithm should be declared in the initialization drawing subroutine. It's easier to make each ensemble member to call a DIM algorithm independently, while it's a challenge that how to drive an ensemble DIM algorithm by all ensemble members in a model ensemble cooperative. To overcome this challenge, the online DIM procedure manager of DefTC will automatically generate an ensemble set component model. This model unifies the processes of all ensemble members and will be used to drive the ensemble DIM algorithm. Thus, the data exchanges between the model, between each ensemble member and the DIM algorithms is performed in two stages. The data exchanges between each ensemble member and the ensemble set. The data exchanges between the ensemble set and the DIM algorithm. The data exchanges operation for each stage can be generated automatically by TCAP2. To advance flexibility, various operations for calculating ensemble values are provided, such as ensemble, gather, average, anomaly, and so on. To further improve flexibility, DefTC enables users to conveniently specify the algorithms, periodic timers, and ensemble operations via an XML configuration file. The ensemble operation can be set to none, which means no ensemble operation. In other words, each ensemble member will call this the algorithm independently on its own processes. DefTC therefore now enables users to flexibly develop a weakly coupled ensemble DIM system, where each component model can use its own DIM algorithm and its own frequency, while ensemble members of a component model can conduct a DIM algorithm separately or cooperatively. So to evaluate DefTC, we developed an ensemble weakly coupled DIM system by combining the widely used ensemble DIM system GSI-NCAF and the original atmosphere ocean wave coupled model FIOLW, where only its atmospheric component model WRF was assimilated. For the first step, we developed the subsystem of WRF by adapting GSI-NCAF to DefTC. Original Wolf GSI encap use offline implementation for ensemble DA, where program restarts are required, and the data exchanges among Wolf GSI observation operator and the encap are achieved via all files. In each D window, there are 3D operations, including GSI observation operator for the ensemble mean for each ensemble member and the encap for calculating the increment. To adapt Wolf GSI encap to DEFCC, the drawing subroutines for the GSI and encap were developed respectively. Thus, the GSI observation operator share the same drawing subroutines but use different configurations of ensemble operation when working for the whole model ensemble or for each model ensemble, each ensemble member. And the 3D operations were initialized and executed in each D window separately by the model. After successfully adapting to DEFCC, the online D system of Wolf GSI encap is generated. Now the program restarts are avoided, and the data exchanges among Wolf GSI and the encap are automatically handled by DEFCC without our files. So to evaluate the impact of DEFCC, we first compared the online and offline D system of Wolf and GSI encap using the Suen region and the different resolutions as well as different time steps. Only one day integration is used with 5 variables assimilated every 6 hours. Four sets of test cases are designed for evaluating the impact of DEFCC and different ensemble numbers, different number of processes, and different resolutions. The experimental results show that the online D system with DEFCC significantly accelerates the Wolf GSI encap when enlarging ensemble size or increasing the number of cores. And the experimental results also show that the online D system significantly accelerates the Wolf GSI encap when the resolution gets finer or increasing the number of cores at the same time. In addition, we find that the online system adapted by DEFCC keeps bit identical result with its original offline system. So, for a brief summary, this work shows that the development of an ensemble D framework can benefit from a coupler, such as DCouple2. Now, DEFCC can effectively help develop an efficient online D system with convenience. So for the future work, we hope there are more applications of DEFCC, and we'll upgrade the DEFCC for supporting the construction of strongly coupled ensemble D system. So thank you for listening.
Thank you, Dr. Sun. So now let's move on to the question. I can see 2 questions. I will read them separately. So the first one is again from Lars Nerger. He said, interesting work. Does the framework actually contain DA methods and observation operators, or does it mainly provide the infrastructure part?
Thanks, Lars. Currently, DEFCC only work as infrastructure, just like a library, and the DA methods work like the dynamic link libraries that can be connected to the framework. So it does not provide any DA methods and observation operators. Yeah, but it can easily to connect to them.
Okay. Thank you. And the second question by Wei Shu, he says, nice work. Any details about the so-called weakly coupled ensemble DA methods you can support?
Thanks. Currently, we did not show the example weakly coupled ensemble system, DA system, but this slide we just show a concept part of this weakly coupled ensemble DA system. After building the online, after generating the online Wolf GSI ENKF, just for the only with the only unique atmosphere model Wolf, and we can easily adapt this this DA system into the FIOLW that couple Wolf and ocean model POM and a wave model mushroom together. So in our paper, we just show some results of such weakly coupled ensemble DA system, but not shown here in this PPT. Yeah. Thanks.
Great. So we have 1 more minute left. I also have a question. I was wondering, you mentioned in the end that you will upgrade it to you have plans to upgrade it to fully coupled, strongly coupled DA. What will be the challenging, potential challenges and issues that you will face?
Yeah, I think the most significant challenge is that, for example, currently we can generate the ensemble set for one component model in a weakly coupled ensemble DA system. But if we try to upgrade to the strongly coupled DA system, we will try to generate an ensemble set for at least 2 component models, where the ensemble of the 2 component models will cooperatively use the algorithm together. So, and also there will be a lot of challenges for data exchange. We just think about that. But fortunately, there is a new national project in China will support this work. So we can finish. We just guess that we can finish this work in maybe 2 or 3 years. Thank you.
Thank you very much.